Okay, here's how I'm going to approach this. We have a tricky issue because of the two O's. So first of all, let's consider words that have the two O's. We could have blank O, we could have O blank O, or we could have O blank. And in each case, we could put one of the five non-O words, one of the five non-O letters in there. And so there's 5 possibilities for each one. So there are altogether 15 words that have two O's in them. Well, now let's ignore the two O's. Now let's just consider the 6 separate letters. And of these 6 separate letters, we're going to pick 3 different letters. So we have 6 choices for the first letter, 5 remaining choices for the second letter, and 4 remaining choices for the third letter. Well, 5 times 4 is 20, times 6 is 120. 120 plus 15 is 135. And that is the number of 3-letter words that we can make.
Okay, to determine the total number of arrangements where Anne and Bob are not seated together, we're going to first determine the total number of arrangements where there are no restrictions whatsoever. From this number, we're going to subtract all of the arrangements where Anne and Bob are seated together. The result will be just those arrangements where Anne and Bob are seated apart. Okay, let's do the first part here. In how many ways can we seat all 5 people without any restrictions whatsoever? Well, we have 5 people here, so let's place our 5 chairs down here. Now we're going to take this task of seating all 5 people and break it into 5 stages. Stage 1 will be to seat someone in the first chair. Stage 2 will be to seat someone in the second chair, and so on. So stage 1, in how many ways can we seat someone in the first chair? Well, we have 5 people, so we can accomplish this stage in 5 ways. Now, once we've seated someone in the first chair, only 4 people remain. So the number of ways to seat someone in the second chair will be 4. Now that we have seated people in both chairs 1 and 2, only 3 people remain, so there are only 3 ways in which we can seat someone in the third chair. As you can see, then there will be 2 ways to seat someone in the fourth chair, and finally 1 way to seat someone in the last chair. So the total number of ways to accomplish all 5 stages will be the product here, which is equal to 120. So there are 120 different ways we could seat all 5 people without any restrictions whatsoever. Now we want to determine how many ways we can seat all 5 people such that Anne and Bob are seated together. How do we do this? Well, to ensure that Anne and Bob are seated together, what I'm going to do here is take Anne and Bob and glue them together so they become one entity. Okay? So now that we have 4 entities, we only need 4 chairs. So one possible arrangement would be this. Another possible arrangement would look like this. And so on. So we have 4 entities and 4 chairs. We'll tackle this using our stage technique. In how many ways can we seat one entity in the first chair? Well, we have 4 entities to choose from, so we can accomplish this in 4 ways. Once one entity has been seated in the first chair, only 3 entities remain, so there are 3 ways to seat something in the second chair, and so on. So the total number of ways to seat all 4 entities will be the product here, which is equal to 24. Now at this point it seems like we're done. However, we've only considered the possibility that Anne is seated to the left of Bob. What about the possibility that Bob is seated to the left of Anne? So we must also consider this arrangement. So once again, we'll take these 4 entities and seat them in 4 chairs. While using the same calculations we did earlier, the total number of ways to arrange these 4 entities will be 24 as well. So now we're done. We now can calculate 120 minus 24 minus 24, which equals 72. So there are 72 possible arrangements such that Anne and Bob are not seated together. So our answer here then is D. Okay, we have 6 children, and we have 6 shirts to distribute among those children. Now there are several ways to distribute these shirts. Here's one possible distribution. Here's another, and another, and another. So we want to come up with some systematic way to distribute these shirts so that we can count them. Here's one approach. Let's choose any 3 children. Now those 3 chosen children will receive red shirts. The remaining green shirts then will go to the children who have not yet received shirts. Let's try that again. We'll choose any 3 children. Those 3 children will receive red shirts, and the remaining green shirts will go to children who do not yet have shirts. As you can see, each new selection of 3 children will correspond to a new distribution of the 6 shirts. So our question then becomes, in how many ways can we choose 3 children from these 6 children? Well, notice that the order in which we select these children does not matter. In other words, selecting child 1, 2, and 3 is the same as selecting child 3, 2, and then 1. So since the order doesn't matter here, we're looking at a combination question. So we have 6 children altogether, and we want to choose 3 of them. We can accomplish this in 6 choose 3 ways. We can now use the following formula to evaluate 6 choose 3. It equals 20, so our answer here then is A.
So we have 3 rooms. We have room A, B, and C. A can be painted orange, red, or green. Room B can be painted orange, white, or red. And room 3 can be painted white, red, or green. And we want to know how many combinations. And the only condition that's not allowed is all 3 rooms being painted the same color. So, fundamental counting principle tells us we have 3 choices for the first, 3 choices for the second, 3 choices for the third. That would be 27. How many of those combinations would not be allowed? Well, the only color that appears in all 3 rooms is red. And so all red would not be allowed. That's one combination we'd have to subtract. That would take us down to 26. Answer choice B.
To solve this question, please consider the following scenario. These are the 10 people in the room, and each person in this room just finished shaking hands with 3 other people. So now when we approach this person up here and ask, how many people did you shake hands with? The person says 3. So far the total number of handshakes is 3. Now we ask this person, how many people did you shake hands with? And the person replies 3. So now our total is 6. This person also says that she shook hands with 3 people. So now the total number of handshakes is 9, and so on. Every single person in the room says that she shook hands with exactly 3 people. So it seems that the total number of handshakes must be equal to 10 threes. However, we've made one small mistake here. Consider these 2 people down here, person A and person B. And let's say that these 2 people shook hands with each other. This means that when we asked person A about the number of handshakes she had, she was including one of those handshakes with person B. Similarly, when we asked person B how many people she shook hands with, she was including that same handshake with person A. So what we've done here is we've counted every single handshake twice. So we need to take our current sum here and divide it by 2. When we do so, we get 30 over 2, which is equal to 15. So our answer is A.